21 ECC 202T Analog and Linear Electronic Circuits. Unit 2 Linear ICs Operational Amplifier. The operational amplifier. An operational amplifier or op-amp is basically a very high gain amplifier used in many electronic circuits. It is called direct coupled because there are no capacitors between stages, so even DC signals can pass through. Inside an op-amp, we mainly have three important sections. First, a differential amplifier which compares two input signals, then a level shifting stage which adjusts voltage levels, finally an output stage which provides the required output power. Since it can amplify both AC and DC signals, op-amps are extremely useful in applications like filters, amplifiers, and signal processing circuits. We commonly abbreviate the operational amplifier as op-amp, which we will see throughout this subject course. Applications of op-amp. The name operational amplifier comes from its original purpose, performing mathematical operations in analog computers. Operations like addition, subtraction, multiplication, and integration are implemented using op-amp circuits. Today, op-amps are not limited to just calculations. They are widely used in many electronic applications. By adding external components like resistors and capacitors, we can control how the op-amp behaves. Op-amp symbol. The op-amp is symbolized with a triangle. It has three main terminals, two inputs and one output. The input marked with a minus sign is called the inverting input, and the one with a plus sign is non-inverting input. We denote V1 as the voltage at the non-inverting terminal, V2 as the voltage at the inverting terminal, and V0 as the output voltage. All these voltages are measured with respect to ground. The symbol A represents the voltage gain of the op-amp, which is typically very large. Usually, op-amp represented using a triangular symbol as shown in this figure. Now, let's look at the practical op-amp symbol, which also include the power supply connections. Practically, the op-amp actually has 5 terminals, 2 inputs, 1 output, and 2 for power supply. The op-amp requires both a positive and a negative power supply to operate properly. These are denoted as V plus and V minus. Typically, the supply voltage can vary from plus or minus 5 volt up to plus or minus 22 volts. However, in most of the circuits, we commonly use plus or minus 15 volt. This dual supply allows the op-amp to produce both positive and negative output voltages. Without power supply, the op-amp cannot function. So these terminals are just as important as the input and output. Next, we will see the op-amp packages. Apart from the internal circuit, op-amps are also available in different physical forms, known as packages. The first type is flat package, which is compact and used in specialized applications. Next is the metal can package, also called TO package, which looks similar to the transistors. The most commonly used one is DIP package, which is easy to mount on circuit boards. DIP or DIP packages comes with different numbers of pins like 8, 12, 14, 16 or even 20 pins depending on the type of op-amp. In most of the lab experiments and practical circuits, we use the 8-pin DIP op-amp such as popular IC 741. Operational amplifier pin configuration. The pin configuration of 8-pin mini DIP is shown as follows. It has 8 pins. The first pin is offset null, second is inverting input, third is non-inverting input, fourth is the negative power supply, fifth is offset null, sixth is output, seventh is positive power supply, and eighth is no connection. Op-amp specifications. All ICs, including op-amps, are designed to work within certain temperature limits. Temperature affects performance, reliability, and lifespan of electronic components. ICs are broadly classified into three categories based on where they are used. Military grade ICs can withstand extreme conditions from very low to very high temperatures. Industrial grade ICs are used in environments like factories where conditions are moderate but still demanding. Commercial grade ICs are used in everyday devices like computers and consumer electronics. For most lab and classroom applications, we typically use commercial grade ICs. Op-amp specifications. The 741 is one of the most widely used op-amp and is internally compensated. Means it is stable without requiring external components for frequency compensation. It is originally developed by Fairchild Semiconductor. Different companies manufactures ICs and each company uses specific prefix codes to identify their products. For example, LM indicates National Semiconductor, SN refers to Texas Instruments, MC belongs to Motorola. These prefixes help us identify the manufacturer and sometimes the series or type of the IC. Even though the prefix changes, the core functionality of the IC, like 741 op-amp, usually remains the same across manufacturers. The MUA 741 op-amp is so popular that it is manufactured by many companies under different names. For example, LM741 from National Semiconductor, MC741 from Motorola, SN52741 from Texas Instruments, etc. Even though the name differ, they all perform the same basic function. Some ICs are further classified into categories like A, C, E, S, and SC. These classes usually indicate performance levels, accuracy, or temperature specification. So when selecting an IC, we should not only look at the number like 741, but also the prefix and class designation. The basic 741 op-amp comes in several variants, each designed for specific requirements. The 741 is typically used for military grade applications, while 741C is designed for commercial use. Versions like 741A and 741E are improved models with better performance compared to their base versions. The 741S and 741SC versions offer a high slew rate, meaning they can respond faster to changes in the input signal. Higher slew rate means the op-amp can handle fast changing signals more effectively. So depending on the application, whether it requires better accuracy, faster response, or wider temperature range, we choose the appropriate version. This figure shows the block diagram representation of an op-amp. It has mainly 4 stages. First one is input stage and it contains dual input balanced output differential amplifier. Then comes the intermediate stage which has a dual input unbalanced output differential amplifier. And next is the level shifting stage. It has emitter follower using constant current source. And the output stage is a complementary symmetry push-pull amplifier. The block diagram representation of the op-amp we can see in detail. The first stage of an op-amp is the input stage, which is a differential amplifier. It takes two inputs and produces a output based on the difference between them. Its main job is to amplify the different signal and reject unwanted common signals like noises. This stage provides most of the voltage gain and also determines how much input resistance and the op-amp has. The output of the input stage is fed into the intermediate stage. This intermediate stage usually converts the signal into single-ended output, meaning only one output is taken with respect to ground. Because the stages are directly coupled, the DC level at this stage is not zero. It is above ground. So the input stage focuses on accuracy and signal comparison, while the intermediate stage focuses on further amplification and signal conditioning. Level translator. After the intermediate stage, the signal may have DC level that is above ground. So we use a level translator circuit to shift this voltage down closer to 0 volts. This ensures that the output is properly centered with respect to ground. Usually this is implemented using an emitter follower with a constant current source. Output stage. The final stage of the op-amp is the output stage. It uses a push-pull configuration. Means two transistors work together, one for positive and one for negative cycles. This improves the output voltage range and allows the op-amp to supply more current to the load. Another important feature is low output resistance, which ensures efficient signal delivery to the load. So the level translator prepares the signal and the output stage delivers it efficiently to the external circuit. This is the basic op-amp internal schematic. Characteristics of an ideal op-amp. To simplify analysis, we often assume an ideal op-amp which has perfect characteristics. The first is infinite gain, meaning even a tiny input difference produces a measurable output. It has infinite input resistance, so it does not draw any current from the source. This means there is no loading effect on the previous stage. The output resistance is ideally zero, allowing it to deliver maximum power to the load. When there is no input, the output should ideally be zero. This means no offset errors. An ideal op-amp can amplify signals of any frequency without losing strength. In reality, no op-amp is perfect, but these assumptions help us to analyze the circuit easily. So, an ideal op-amp will be having infinite gain, infinite input impedance, zero output resistance, and perfect response. Another important ideal characteristic is infinite CMRR. This means the op-amp completely rejects any signals that are common to both input like noises. Only the difference between two input signals get amplified. CMRR is defined as the ratio of differential gain to the common mode gain. Next ideal characteristic is slew rate, which tells us how fast the output can change. In an ideal op-amp, the slew rate is infinite, meaning the output responds instantly to the input changes. In practical op-amps, this is limited, which can affect high frequency performance. So CMRR ensures noise rejection and slew rate ensures speed of response. The table shown here summarizes the ideal operational amplifier characteristics. So the voltage gain will be infinity, input resistance will be infinity, output resistance and output offset is 0, bandwidth CMRR and slew rate will be infinity for an ideal operational amplifier. Characteristics of an amplifier. Even though the op-amps have very high gain, the output cannot increase indefinitely. It is limited by the supply voltage. This is called saturation. On the positive side, the output cannot reach exactly plus VCC but stays slightly below it. Similarly, on the negative side, it cannot reach exactly minus VEE but remains slightly above it. If we plot output versus input, we get the voltage transfer curve as shown in the figure. Near zero input, the output changes linearly, but as the input increases, the output quickly reaches saturation and becomes constant. This behavior is very important in applications like comparators, where the output switches between saturation levels. Next, we are going to see the open loop configurations. The open loop op-amp work without feedback. The output is completely independent of the input after amplification. So there won't be any feedback path. Because of very high gain, even a small input voltage can drive the output to saturation. No feedback path. If there is no feedback path, the main characteristics of op-amp is very high gain, typically 10 to the power 5 or more. Output usually goes to plus Vsat or minus Vsat, acts like a comparator. Not commonly used for linear application due to instability. Differential. There are mainly three types of open loop op-amp configurations. They are differential amplifier, which amplifies the difference between two input signals, inverting amplifier, input applied to inverting terminal. The output will be of 180-degree phase shift. Non-inverting amplifier, input applied to non-inverting terminal, so output is in phase with the input. Open loop inverting amplifier. The figure shows the open loop inverting amplifier configuration. So in this, there is no feedback is present. Input is given to the inverting terminal, which causes inversion. Non-inverting terminal is grounded, that is V1 is equal to 0. Input applied at inverting terminal, V2 is equal to Vi. Output depends on the difference, that is V1 minus V2. This results in a negative output. This negative sign indicates the output is 180-degree phase. Output is at 180-degree phase shift with respect to the input. Even a small input leads to large output due to high gain A. In open loop mode, the amplifier quickly reaches saturation, so it behaves more like a comparator than a linear amplifier. Next is open loop non-inverting amplifier. The figure shows the open loop non-inverting amplifier. Here, the input is given to the non-inverting terminal. Since there is no feedback, this is an open loop configuration. Input is applied directly to V1. So V1 equal to Vi, and inverting terminal is grounded. So the output depends on the difference V1 minus V2. So the result will be a positive amplified output. The output follows the same polarity as input without any inversion or with zero phase shift. Due to very high gain A, even a small input drives the output to positive or negative saturation. Next, let us look into some of the problems. Determine the output voltage of an open loop inverting amplifier for the following inputs. Input voltage is equal to 10 millivolt DC. Input voltage is equal to minus 30 microvolt peak sine wave. So given the op-amp is 741 with open loop gain, A is equal to 2 into 10 to the power 5 and saturation voltage is plus or minus 12. So we can calculate the output voltage, that is Vout is equal to A into Vi, where A is the open loop gain. For DC input, Vout is equal to minus of 2 into 10 to the power 5, 10 into 10 to the power minus 3, that is equal to minus 2000 volt. But the op-amp cannot give this output because it will be saturated at some voltage which is lesser than the supply voltage. So since it is given that the saturation voltage is plus or minus 12 volt, our output voltage will be minus 12 volt. For AC input, Vout is equal to minus 2 into 10 to the power 5 into minus 30 into 10 to the power minus 6, which is equal to plus 6 volt. But op-amp cannot give the output within saturation limits. So the final answer will be plus 6 volt peak sine wave inverted phase already considered. Next is closed loop configurations. So here the feedback is included in the configuration. In open loop, even a tiny input causes very large output. This leads to saturation. So this is not useful for amplification. Why we are going for negative feedback? The feeds part of the output back to input. This reduces the overall gain, makes the system stable and predictable. So usually whenever we consider an op-amp circuit, we follow some golden rules. One is input current is 0 and voltage difference between input is 0. That is virtual short. Because of the feedback, the op-amp adjusts its output such that V plus is almost equal to V minus. So this virtual short is not a real short, but it represents only the voltage equality. Closed loop configuration. There are 4 commonly used closed loop op-amp configurations. Those are inverting amplifier, non-inverting amplifier, voltage follower or unity gain buffer and differential amplifier. Next we are going to see about inverting amplifier. The figure shows the inverting amplifier. The circuit is called inverting amplifier because the output signal is 180 degree out of phase with the input signal. It is one of the most widely used closed loop op-amp configuration. Here R1 and RF determines the output voltage. The ratio of the RF by R1 determines the voltage gain. The virtual ground concept says that due to very high open loop gain of the op-amp, the negative feedback, the voltage difference between the two input terminals become nearly zero. Since the non-inverting terminal is connected to ground, the inverting terminal also appears to be at 0 volt. However, it is not physically connected to ground. So it is called virtual ground. Then ideally we consider the input current to the op-amp terminals as 0. So we consider I3 equal to 0. To derive the gain equations, we consider the Kirchhoff's current law. So here by applying the Kirchhoff current law, we can get I1 equal to I2 plus I3. Since input current to the op-amp is negligible, that is I3 equal to 0, we can get I1 equal to I2. Current through the input resistor can be found out as Vin minus V2 by R1. And current through the feedback resistor RF can be found out as I2 is equal to V2 minus V0 by RF. As the inverting terminal is virtual ground, we can consider V2 is equal to 0. So by substituting V2 equal to 0 in the above equations, we can get Vin by R1 is equal to minus V0 by RF. By rearranging the equation, we can get Vout is equal to minus RF by R1 into Vin. Hence the closed loop voltage gain ACL of an inverting amplifier is equal to V out by Vin, which is equal to minus Rf by R1. The negative sign in this gain equation indicate the output of this inverting amplifier will be having 180-degree phase shift with respect to the input. Next we are going to see the non-inverting amplifier. This circuit shows the non-inverting amplifier. The input signal is connected to the non-inverting terminal of this op-amp. The output signal will be in phase with the input signal. That means there won't be any phase inversion. The derivation of closed loop gain. By applying the Kirchhoff's current law at node V2, we can get I2 equal to I3 plus I1. Hence, the input current to the op-amp is negligible. We can consider I3 is approximately equal to 0. Therefore, I2 equal to I1. Current through the feedback resistor can be found out by I2 equal to V0 minus V2 by Rf. And current through the input resistance R1 will be equal to I1 equal to V2 minus 0 by R1. Since V2 equal to Vin, we can substitute that in the above equation and we can get it as V0 minus Vin by Rf is equal to Vin by R1. Rearranging the equation, V0 equal to 1 plus Rf by R1 into Vin. So if we see the closed loop gain of this configuration, ACL will be equal to V out by Vin is equal to 1 plus Rf by R1. The gain is positive, which indicate the output signal will be in phase with the input signal. Next is voltage follower or buffer amplifier. The voltage follower is also known as buffer amplifier or unity gain amplifier. It is a special case of non-inverting amplifier circuit configuration. So here the output terminal is directly connected to the inverting input terminal. Hence there is complete negative feedback is provided. Since the output is directly fed back, the output voltage becomes equal to the input voltage. Therefore, the voltage gain is unity. Important characteristics are very high input impedance and very low output impedance. And there is no phase inversion and gain is equal to 1. The main uses of voltage follower is for impedance matching. It prevents loading effect between stages of the circuit. It acts as buffer between a weak source and a load. So we can use wherever we want higher input impedance and lower output impedance. Next is differential amplifier. The circuit is called differential amplifier because it amplifies the difference between two input voltages. In ideal operational amplifier, the current entering both input terminals is assumed to be 0 due to infinite input impedance. So the currents I2 and I5 are very negligible. So by applying the Kirchhoff current law at node V1, we can get I4 is equal to I5 plus I6. Since I5 equal to 0, we can get I4 equal to I6. Then by using Ohm's law, Vn minus V1 by R1 is equal to V1 by R2 and just rearrange the equation to get Vn1 by R1 equal to V1 by R1 plus V1 by R2. Hence the voltage at node V1 is obtained as V1 is equal to Vn1 R2 by R1 plus R2. For an ideal op-amp, the differential input voltage is 0. So we can get the difference between V1 and V2, that is Vd equal to 0. So the voltage at both input terminals are equal. So V2 equal to V1, which is equal to Vn1 R2 by R1 plus R2. Then apply the Kirchhoff law at Kirchhoff current law at V2. So I1 equal to I2 plus I3, but the input current to the op-amp is negligible. So we can consider I2 is equal to 0. Therefore, we can write the equations as V in 2 minus V2 by R1 is equal to V2 minus V0 by R2. By substituting the value of V2, we can get V in 2 minus V in 1 into R2 by R1 plus R2 by R1, which is equal to V in 1 R2 by R1 plus R2 minus V0 by R2. Simplifying the equations, and after rearranging the terms, we can get the output voltage expression as R2 by R1 into V in 1 minus V in 2. A differential amplifier ideally amplifies only the difference between two input signals. When both input voltages are equal, the difference becomes 0. Hence the ideal output voltage is also 0. However, practical op-amps are not perfect and may produce a small unwanted output even when both inputs are same. The signal that is common to both inputs is called common mode signal. The average value of the two inputs voltages gives the common mode voltage. The difference between the two input voltages is called differential mode signal. Using these definitions, the individual input voltages can be expressed in terms of common mode and differential mode voltages. These relations are useful in the analysis of the performance of practical differential amplifiers and calculating the parameters such as common mode rejection ratio or CMRR. So the common mode signal is defined as the average of two input signal, as we told, that is VCM equal to V in 1 plus V in 2 by 2, and the differential mode signal is VID is equal to V in 1 minus V in 2. So by rearranging the equation, we can get V in 1 is equal to 2 VCM plus VID by 2. Similarly, we can derive the expression for V in 2, that is 2 VCM minus VID by 2. The output voltage of practical differential amplifier depends on both input voltages. The gain A1 represents amplification from the non-inverting input when the other input is grounded. Similarly, A2 represents the amplification from the inverting input when the non-inverting terminal is grounded. So we can get it as the output of the differential amplifier V out is equal to A1 V in 1 plus A2 V in 2. So by substituting the expressions for V in 1 and V in 2, we can get V out is equal to A1 into 2 VCM plus VID by 2 plus A2 into 2 VCM minus VID by 2. By simplifying this equation, we can get the V out as A1 plus A2 into VCM plus A1 minus A2 by 2 into VID. The output voltage can therefore be written as V out is equal to ACM, that is A1 plus A2. We are substituting ACM, A1 plus A2 with ACM into CM plus A1 minus A2 by 2, that is ADM into VID. So we can write it as V out equal to ACM into VCM plus ADM into VID. The common mode gain is defined as ACM equal to A1 plus A2, and the differential mode gain is defined as ADM is equal to A1 minus A2 by 2. Next, we are going to see common mode rejection ratio. The common mode rejection ratio is defined as the ratio of differential mode gain to common mode gain. That is CMRR is equal to ADM by ACM. The higher CMRR value indicates the better rejection capacity of the op-amp for the unwanted common mode noise signals. Next, we are going to see some of the numerical problems. If you consider a differential amplifier which has R1 equal to 10 kilo ohm, R2 equal to 100 kilo ohm, and Vin is equal to 0.2 volt, Vin2 equal to 0.5 volt. Find the output voltage. So the output voltage equation for a differential amplifier is given as V out equal to R2 by R1 into V in 1 minus V in 2. So if by substituting the values, we can get it as V out is equal to 100 kilo ohm by 10 kilo ohm, into 0.2 minus 0.5. So that is equal to 10 into minus 0.3, which is equal to minus 3. Next, for a non-inverting amplifier, it has R1 equal to 1 kilo ohm, RF equal to 9 kilo ohm, Vin equal to 0.2 volt. Find the output voltage. So for a non-inverting amplifier, the output is given as Vin into AV. So AV is given as 1 plus RF by R1. So by substituting the values, we can get it as 1 plus 9 kilo ohm by 1 kilo ohm, that is equal to 10. So the output voltage is equal to gain into input voltage, that is equal to 10 into 0.2, that is equal to 2 volt. These are the references used for this video. Thank you.